This video belongs to the book Statistical Modeling with R that I wrote and was published by Oxford University Press in 2023. Today I'm going to talk about GLMs for a specific type of response variable, that is a response variable that has positive and real values. We start again as usual with exploratory data analysis, to be followed by the fitting of the same model with the Frequentist and the Bayesian approaches. The data and codes can be found in the website shown in the screen. So some response variables such as body masses, sizes, salaries have positive real values. So the log normal distribution here shown for different values of the mean and the standard deviation could be used to model this type of data. We did so in the context of the general linear model by transforming this response variable with logarithmic transformation, and the log of this response variable then had a normal distribution. So the gamma distribution, here shown in one of its many possible ways of framing it, belongs to the exponential family of distribution, and here is shown for its two parameters, mu and the dispersion parameter phi. This distribution has a variety of shapes that ranges from the negative exponential, which is a special case of the gamma distribution for some parameters, to a very symmetrical parameter shape for some values of the parameters. So the phi, the dispersion parameter of the gamma distribution, governs the relationship between the mean and the variance, and here we see that the mean is proportional to the variance, and that concept of proportionality is dictated by the value of the parameter phi. The GLMs that use a gamma of whose response variable is modeled with a gamma distribution can have either of two link functions. The canonical link function is the inverse link function. Please see the books for the details. However, this canonical link function is rarely used because it can, in some cases, lead to incorrect predictions of the mean of the response variable. So the more often used link function is the log link function, which is the one that we are going to use here in this video and in the book as well. So the idea of this analysis is to predict the seedling biomass for some tree species in Malaysia based on the diameter, height, and the number of leaves. So I start as usual by importing the data. This is the complete data set that we are going to use. We have a large number of data points for different species. We are going to ignore the fact that we have many data points for different species or genus. We are simply going to consider the biomass as the response variable, the height, the leaves, and the diameter for the purpose of this model. So we standardize the values of the numerical explanatory variables to compare the effects on the scale of the link function, which is log in this case, and we generate a data frame that contains these scaled and standardized values of the numerical explanatory variables, and the response variable biomass as well. So we use, as always, the cumulative distribution function plots and the QQ plots to compare three candidate distributions. In the first of the two plots, the three candidate distributions are as seen: the log normal, normal, and gamma. In the cumulative distribution function, we see that the three distributions are pretty similar, and it's almost impossible to discern them, to differentiate them, whereas this is a lot clearer in the QQ plot, in which we see that the gamma distribution is better than the log normal and the log normal distribution. So in some cases, the log normal distribution that has another particular relationship between the mean and the variance would be better than the gamma. So these should be assessed on a case-by-case basis. So the statistical model is that the response variable follows a normal distribution with a mean and a dispersion parameter, and we use the log, not the logit link function for this purpose. So we are going to assess the relationship between the explanatory and the response variables. Here showing in the bottom row that the biomass is actually positively related to the height, number of leaves, and diameter, and that none of these numerical explanatory variables are highly correlated. By highly correlated, we mean a correlation coefficient higher than 0.7 in absolute value. Therefore, we can include all of them as explanatory variables in the models. For the frequentist model fitting, we simply use the command GLM of the package stats that is loaded whenever you start a session in R. Here's the response variables and the numerical explanatory variables. And for the family equal gamma, we must specify that the link function that we are going to use is log. Otherwise, we would use by default the inverse, the canonical link function, which is inverse for this probability distribution. So here we have, for the three numerical explanatory variables, we have the partial slopes. Because the variables were standardized prior to the analysis, we can actually state that changing one standard deviation in the number of leaves is in the diameter is 5 times more important to determine the log of the seedling biomass than compared to the number of leaves, by just making the ratio of 0.43 divided by 0.08. All these partial slope happen to be statistically significant. The intercept is the log of the mean of the response variable when each of these explanatory variables is 0, and because they were standardized prior to the analysis, this corresponds to the log of the mean seedling biomass when these explanatory variables are in their mean values. The percentage of deviance explained is pretty high. This model explains 83.8% of the deviance of the response variable. So in order to assess the goodness of fit, as usual, we use the package Broom, and then we simulate the Dunn-Smyth residuals, and these simulated Dunn-Smyth residuals are converted to a normal distribution. Again, these are input into the data frame resid.m2, with which we make the following plots. So in the plots A, B, C, D, and E, we essentially see a more or less random scatter without any clear signs of trends of any sort, which suggests that the model has fit well to the data. Likewise, we see in the QQ plot that these converted Dunn-Smyth residuals do indeed have a normal distribution, and that there might be 3 points out of 300, that is 1% of the points, that might have an important influence in the estimated parameters. We predict, but we have not demonstrated, that by changing just 1% of the data, 3 out of 300 points, is unlikely to change significantly the maximum likelihood estimate shown in the previous slide. We can obtain the conditional curves, and which are the relationship between the seedling biomass and the diameter, by keeping the other variables, height and the number of leaves, to 0, that is to their mean values. This is what plot A says, and plot B is likewise the similar relationship between the seedling biomass and the height, while keeping all other variables to their mean values. And here we have simply the parameter estimates under 95% confidence intervals. The Bayesian model fitting, the statistical model includes the partial slopes of determining the mean of the response variable, and the shape coefficient the shape parameter of the gamma distribution is this phi coefficient, and we are going to use a log-link function. So what I did is I defined the priors in the normal case, are pretty weak priors for the partial slopes, and these are values of the log of 70 for the mean biomass, for the mean of the prior for the intercept, and this standard deviation for the in normal distribution, that is going to be the prior distribution for the slope, for the intercept, sorry. So here is what implies the prior for each of the two parameters that I just modified. In order to fit the model, simply we use the formula which is simply the response variable and the numerical explanatory variables, the data set that we are going to use a log-link function with this gamma distribution, the priors that we just set, and the usual attributes that we have been using for the Hamiltonian Monte Carlo along this book and set of videos. The coefficients, so the summary includes the marginal posterior distributions for the intercept and the partial slopes for each of the explanatory variables. Here are the means of these posterior distributions. Here are the 95% credible intervals for each of these distributions. Likewise, we obtain the shape parameter of the gamma distribution and its 95% credible intervals. There are hat coefficients for all the parameters are close to 1, which is a sign of a very good that the three chains that we have used converge to the common posterior stationary distribution, and the large number of the effective sample sizes says that we have a very large number of effectively statistically independent values in each of the chains. The means of the posterior distributions, the marginal posterior distribution could be compared because we have standardized the values of the explanatory variables, and therefore we can say that changing one standard deviation in the number of leaves is almost 5 times less important in determining a change in the log of the mean seedling biomass than changes in one standard deviation of the diameters of the trees, if that were possible to change in an experimental manner. So the posterior distribution suggests for the parameters suggests that all three parameters have converged. The three chains have converged to a common posterior distribution for all parameters. The autocorrelations are all pretty small. You please don't overjudge this unwidely seemingly high coefficient, high autocorrelation, because this is an autocorrelation of 0.1 for values separated, for parameter values separated by one step in this chain, but not in the other chain. So by and large, we obtained a large number of statistically independent parameter estimates sampled in each chain of this Bayesian GLM. The goodness of it is assessed with the Dunn-Smyth residuals based on the posterior predicted distribution. Here it is. This posterior predicted distribution is an input for the command create Dharma of the Dharma package. Here it is. And with the observed values and the median of the predicted values, we obtain the raw Dunn-Smyth residuals that are converted to a normal distribution. And then we create, as usual, a data frame with all the input necessary for the analysis. And this includes these converted Dunn-Smyth residuals, the explanatory variables of the model, the fitted value, the average fitted values, and the Pareto K coefficients. So this model explained a pretty large percentage of the variation of the response variable, 85%. So here are the plots, and the plots are more or less satisfactory. That is, plots B, D, and E are pretty good, showing a random scatter of the residuals for different values of the explanatory variables. Plot A show more or less a triangular shape. This more or less of triangular shape indicates a heterogeneity in the values of the residuals that are very large variation of the residual for low values of the fitted values of the fitted the predicted values of y, whereas this variation decreases as we increase the predicted value of y. This suggests a heterogeneity of the variation in the residuals, suggesting that the model might need some extra parameter or structural modification, one of which could be add explanatory variables to the dispersion parameter phi of the gamma distribution. This is something that we can do. In the plot E, more or less, we see an indication of this triangular shape that we saw on plot A. Nevertheless, the transformed Dunn-Smyth residuals do have a normal distribution as a sign of a good, well-fitting model, and all points in this data set have are in the very good range, suggesting that none of them have an unduly large influence on the posterior distributions of this model. The conditional curves obtained with the command conditional effects of the package BRMS allow us to draw the following curves. This is the relation between the seedling biomass and the diameter while keeping all other variables to 0, that is to their mean values. And likewise for our plots B and C. And here we have the mean of the posterior distribution for each of the parameters, and their credible interval is so small that cannot be seen underneath the point, but they do exist, as we saw in the summary of the model. So in this video I have talked about the fitting of a GLM when the response variables are positive real values, started with an exploratory data analysis and the Frequentist and Bayesian model fitting. I hope you found this video interesting, and I thank you for your attention. Bye then.